Okay, yes. Yeah, so above all, I'm interested on this how and why, what is really going on in the brain. So briefly in my talk, I will explain the motivation, why we need to do this. Then I will go through some evidence and methodological advances in interpretations of the data. I will introduce the concept like why we need to look at the brain as a dynamical system, particularly at the macroscopic level, and different mechanistic scenarios, more than one, for the observations that we are seeing. And then I will show some new results that I am getting. I don't want to spoil it. So at a very big picture, we have a structure function problem. We have a structure, a physical structure, which is the brain. And on the other side, we have cognition and behavior, right? And we have what links these two. We have this infinity of patterns that link with cognition and behavior. And when something like we still don't know how to link this, right? But it's important because whenever something here is going wrong, at the level of activity, we need to understand what, but we have psychiatric syndromes, cognitive impairment, and disorders of consciousness, and this alone accounts for more than 10% of the population. So of course, it's a huge problem, a real problem. It's not about the hard problem of consciousness. It's really and any advance we can make in this direction is a contribution for humanity, right? And the thing is, we still don't fully understand what are the mechanisms, the governing rules, the organizing principles. As we heard today, and we will continue to hear, and in the textbooks, there are many mechanistic hypotheses, but the feeling I have sometimes is that maybe we should start challenging some dogmas or questioning some things, some assumptions, revisit old theories, do something, because we need to advance, and at this level, it's evolving very slowly. Well, in my research, I'm mostly interested in dynamic signatures of cognitive function that we detect with both EEG and MEG or with functional magnetic resonance imaging. So these are signatures of brain activity that are more macroscopic, right? So they, as we heard today, like they span several million, even a voxel in fMRI has like millions of neurons. Sorry, let me go back here. Also, I will not be talking about spikes, but sometimes the signals we detect is oscillations, and also the fact that this is distributed activity. So this is not really just a focal response in a single brain area, but more at the macroscopic level and distributed. Okay. I will focus specifically on this today in my talk, as I've explored different things, but one thing that is really intriguing is this story of resting state networks. Some people say they don't believe in it, but I will show you some results and some data, and they are there and they are consistently there. So these are these ultra slow fluctuations in the signals captured in the magnetic resonance scanner, okay, over time. They fluctuate below 0.1 hertz, and they correlate. They are across distant regions, and they are organized, and they organize in these distinct modes of activity. And they reveal subsystems that are activated in different tasks. For example, this would be the sensory motor or the auditory or the visual. But there's also some patterns that appear more during resting states, this so-called default mode network or a control network. I like that at the time, Marcus Reichel called this the brain's dark energy. Or 2010, but this was when I was doing my PhD. But the thing is that since then, despite the evidence, we haven't fully understood where these patterns come from. So over the years, I mean, I remember in 2009, there was already a dedicated conference only on the default mode network. This is getting more or less attention, but there is growing evidence relating these patterns with cognitive performance, with emotional and behavioral scores. They are altered in psychiatric syndromes, in neurological disorders, in disorders of consciousness. Even now in psychiatry, they are being proposed really to be, let's say, they call it neural circuit taxonomy, but they are established patterns that relate with the psychiatric symptoms. So it's important to understand. So they have a function. This is the point I want to make. but their organizing principles remain unclear. So there are different ways to look at these modes. We can see them as activity maps. Okay, so some areas in the brain whose signal co-activates together, as networks. As we say, we can parcellate the signals in the brain, then compute correlation matrices, covariance matrices, then get eigenvectors of these matrices, get different things to see which are the regions that are connecting together. Or we could also look at them as fields, and then depending, there are different approaches. If we just parcellate and look at this from vector field approaches, or if we inflate the brain and look only how they look at the cortical surface. I like to keep the anatomy behind because I like to see how these different places where the signal activates together relate with the macroscopic anatomy. But the thing is that there's a lot of methods. Every year comes a new method, or every month. There are papers just showing, okay, if we do complex PCA, we detect then there's a debate of how many there are, which method detects more similar patterns to the others. But overall, the thing is, all these different methods, they converge to a repertoire of modes, a discrete repertoire, we don't know the number, that are defined in space. And the idea is to try to understand how do they behave in time, okay, to understand better what is going on. So when we look, so here is an example of just to give you an idea of how the fMRI signal looks like, and it's super noisy. So these are different slides. This is from the bottom to the top of the brain, okay? And I'm just plotting here the signal relative to the mean. So I just removed the mean signal. This is pre-processed data already. Pre-processed, like we can go. So they are all aligned to a common template. There's some spatial smoothing, something. But what we look at this, and this looks like noise, right? But when you look a lot to these type of patterns, let me see if I can interact with, well, because usually I can pause. How do I? Sorry, I need to do it like this, okay? So there are some points in time, and here I want to highlight this, where we see this signal here is co-activates with the signal here and with the signal here. And then there's another time point where we see a similar pattern here, right? Here in the front. There's also some signal here in the middle that I like to call the attention. Also, like here, some time point later, we see again some patterns. Sometimes we see a negative version of the pattern. We see it in blue, you see it decreases below the mean. Here again, it's a negative version. Okay, so, but the thing is, so these are occurring very, very briefly in time, and sometimes also we can see it again. Here, just to highlight a point where I could see it in another network, okay? So you see, let's move this around. Okay. So I want to make the point is there are these consistent patterns, and they are not continuously there. So I will go back to the presentation mode. Okay. Yeah, okay. And yeah, so is this noise? What does this have any meaning? So a lot of people have been looking at functional networks or networks just looking at the static correlation, right? So you take for each seed, for example, you look at the signal in the others. And for example, here, the correlation between these two seeds is 0.55. So you can get the seed map. And here it highlights which areas mostly correlate with these different areas of the brain, which other voxels. But if we look at the signal here, okay, maybe here, the time point I was showing here, in some points it's more correlated, but in other time points it's even anti-correlated. So it's not a static. So these correlations are not constant in time. And this is a concept of the dynamic nature of functional connections that I think has been on for the last maybe 10 years of the dynamic functional connectivity. There are different approaches. So some is like to use windows. Let me see, to use different windows, for example, 1 minute, and you compute the correlation matrix of the signals, or another window, and you see, so there they are different. There's a lot of variability, and some people then cluster these windows, but this is quite noisy, and the results depend a lot on the window size. There has been some debate. There are like 3 big papers discussing whether dynamic functional connectivity makes sense or it's just people trying to make sense out of noise. Okay. And then in 2012, so this relates here with the phase extraction. I don't know how. So there was this proposal to, instead of doing the correlation over long windows, or how much can we detect instantaneous interactions. So the idea was to use instantaneous phase synchronization, and for that we have to get the Hilbert, the phase of the fMRI signal or the Bolt signal at each instant of time using the Hilbert transform, and then calculate the cosine of the phase difference at each time point. Okay, we get a matrix. You can narrowband filter, okay, but then there was this debate. It's it from 0.04 to 0.07 hertz, so because the signals are quite slow. And the thing is, when you filter in a given frequency band, sometimes you detect differences between conditions only because the different conditions, some have the more faster dynamics, and so we are missing it. And I did several tests over time, and these fluctuations are there, and with the temporal resolution that if we just apply the Hilbert, even without narrowband pass filtering the signal, we get phases that are meaningful, okay? But the thing is meaningful. So if we do this over time at each time point, this is super noisy, right? It's very noisy. How do we compare this between conditions? There's a lot of false positives. It's very weakly replicable. So is this any meaningful? So at some point, maybe I would like to test your generalized phase extraction from the signals. But because all the rest I think could still apply. The thing is that this instantaneous phase coherence matrix is a rank 2 for the mathematicians who are here. So it can be reconstructed with only 2 eigenvectors, and it's symmetric, so the eigenvalues are real. So basically, if this is eigenvector 1 times its transposed multiplied by the eigenvalue plus the second one, we get a matrix that is exactly the same as the other one. So we can reduce a lot the number of elements that we need, a lot of the noise, by just considering the eigenvectors of this matrix. And in particular, we found that I tested with one or both, just considering the leading eigenvalue, the eigenvector, let's say, the one with the largest eigenvalue, has a meaning, and I will show you this. So what we do is at each instance of time, we have the phases of the signals. Here I'm just plotting them according to their phase portrait, right? So these would be 90 brain areas, so we have 90 phases. We get the eigenvector. Here I'm coloring the areas according to their projection to this leading eigenvector of phase coherence, right? So it's the leading eigenvector of this matrix. And what we find is that all the elements in the eigenvector that have the same sign go together in phase, or at least in the same plane, right, 180 degrees, or project in one direction of the eigenvector. And there are sometimes, not always, I'll say, some areas that shift out of phase from the rest of the brain. So we make a convention that the majority is always like negative, and we have some brain areas whose signals shift out of phase from that. When we do this, okay, we get this eigenvector for each time point, okay, like this. So you'll see this red like areas are the areas shifting out of phase from the rest of the brain. And so we can plot these dynamics, like just the links here are links between areas whose signal shifted out of phase from the main direction. Again, this looks very noisy, but if we cluster this, I'll see what you get. So we have all these eigenvectors, like I showed now, but we concatenate across all the data sets we have. We've applied this method to several different types of data sets, but sometimes we have 180,000 time points, okay, eigenvectors for thousands of subjects, and then we cluster all these eigenvectors into some. It will give, if it's to k equal 5, it will give us 5 cluster centroids, 5 clusters that are represented by their cluster centroid. So when we look at the cluster centroids, so the first one, or here they are sorted according to their probability of occurrence or over time, the largest is always all elements have the same sign. Okay, so it's I call it the global mode. And then we have other networks. I will go a bit more detail, but the cluster centroids here, they reveal the default mode network, the lateral frontoparietal, the somatomotor, the visual. So for example, here is for k equal 8. I've been optimizing the algorithm, now doing it also in voxel space, everything. But here I will show you the results we get, for example, for k equal 8 from a data set with 1,000 scans. So the first mode, or the first cluster of eigenvectors, is this global mode where all the signals are in phase, so I put them all in blue. But then the second one, the most probable, is here from bottom to the top. We clearly see here the default mode network. If I render these areas in red, it overlaps with the known resting state networks. Here the visual, so we see here this activity, so the signals in some brain areas shift out of phase, the ventral attention, the limbic mode, which is called, so the signals in all these areas in the brain shift out of phase, somatomotor. This one, the frontoparietal, is the one they call here as the control system. I will come back to this. That's why I'm insisting on the default mode network and this, because they seem to have, and the dorsal attention. So there is a clear overlap between the networks we see here and the networks we're getting in LIDA with this leading eigenvector dynamics analysis. So the idea is there's something meaning. We're talking about the same thing, okay, at least with this method. With this method, when we cluster, the advantage is that we can then, for each scan, we can go back to the scan and we can know in which time points given the dynamics was assigned to that cluster, right? So for example, here, all these time points in blue were assigned to this cluster state that was representative of all. And we can apply measures from dynamical systems theory as occupancy, for example, which is the proportion of time points assigned to this state, or the dwell time, like once you enter in a given state, how long you remain there. And this allows to obtain single scan metrics that are different from the graph theoretical metrics or others, where you can really compare conditions according to the probability of occurrence of that specific mode, okay? And then, so in a way, this brain activity that I was saying there can be seen as a trajectory in a state space. Imagine each of these crosses is one of these networks, and over time, we're just exploring this repertoire of states in a way and approximating more some cluster centroids and the others. Okay, so using this type of approach, this type of trajectory, we can do, for example, Markov chain transition probability matrices, which is what's the probability of once you are in state one, remaining in state one. Okay, so here the probability of remaining in a given state is a diagonal. So we see that it's larger probability than to switch to any of the other networks. But also whenever you switch to any of these networks, these upper networks, there's always more probability to return to state one than to switch to any of the other networks. So these arrows are stronger, right, to return. So in a way, this could be in this strange attractor, but and this could be kind of ghost attractor. So this was the idea to apply some measures from graph theory. I'm trying to remove this floating thing from here. And so this is an approach just to illustrate that seems to be working, because then we can characterize this for healthy subjects. And in a way, from this perspective, these resting state networks represent a repertoire of pseudo attractors in brain connectivity. We still don't know what they mean. And according to this technique that seems to be giving a lot of significant results, the global mode is also one of them. Yeah.
How does that correlate with like behavior? Because if you have this
yeah.
But we're aggregating a lot of information there from all the data that you have, and then you do that over time, and then you get these eigenvectors, and then you can identify the network, right?
Yeah.
Does that correlate, you know, when you have like this control network or this visual network, does that correlate with behavior, like the ones like
yeah.
Like
so far, it's resting state. So it's spontaneous activity, and it's like a dynamical system where from time to time you see these networks appearing or disappearing. And now we're going to compare. The thing is, are these dynamic features relevant for cognitive function or behavior, let's say? But most of them are in resting state, and I will show I have some studies on tasks which are, for example, listening to music or watching, thinking of positive things. So the first paper where we developed this method was with healthy older adults that were categorized according to their cognitive performance. They did several, it was a sample of 4,000 subjects, and the best cognitive performance and the worst were called for scanning, like the 60 best and the 60 worst. And at the time, I mean, I wasn't really sure what was going on, but we found that indeed the people with higher cognitive performance had more global mode. Okay, this fundamental mode occur more often and less of these other networks. Then, for example, we applied it to a data set from schizophrenia with 150 patients and controls. And indeed, people with schizophrenia spend less time in the fundamental mode or global mode or whatever it is, and they switch more erratically to this other mode. So there were increased excursions to visual, somatomotor, limbic. So there could be something. Also, they have less, what? Sorry, going back. They have less of the default mode network here. Appears less, or they remain less in that state. How do we define the number of modes? And here is a bit also the question, like no one really knows. We could apply some silhouette score or other things, but the approach we do now is, okay, we have a data set. For example, here we had downloaded a database where we have scans from 580 typically developing controls, so children, adolescents, and also young adults, and 437 age and gender matched autism spectrum individuals. This is from the ABIDE database. They were subdivided initially according to if they had Asperger and pervasive developmental disorder. But just to give you an idea, we had to retract the paper because it's not allowed to use the term Asperger anymore because so we put them all together. Because apparently it was not. I mean, there are like ethical issues on those categorizations. We correlate now with scores. So now the correct thing is correlate with IQ, with social things, and yeah. But overall, what we can do is, okay, so for k equal 2, you get two patterns and they overlap. This is the global, and then it overlaps with this ventral attention or other thing. And then for each one, we compare between controls and autists. Okay, here for k equal 2, we didn't find differences. K equal 3, also no difference. So if it's black, it means that there was no significant difference. The p-value is above 0.05. If it's red, here is the plot of the p-values for the different number of states. So this line here, everything above, this is the 0.05 line. So it means everything above is not significant. The red here, the red and the green could be false positives due to multiple testing. Anything that is in blue, this is the Bonferroni corrected threshold, correcting by the number of comparisons. So when we see p-values of 10 to minus 7, we can be confident that this is strong. So here, I don't know if you can see, but this one, here, for K from 11 to 17, we detect here a network that consistently overlaps with the default mode network that is significantly decreased in autism. And we also see another one here that is the lateral frontoparietal. I will go into more detail. So this is a completely data-driven analysis. I asked just the algorithm, what is the pattern of phase relationships, here they are ordered, that better distinguish the two groups. It's significant, doesn't mean that there is really not, the standard errors don't overlap the bars, but these are the standard deviation. But if we look really at it in voxel space, so it's clearly the default mode network. Here I overcompute the correlation with networks from the reference, a spatial pattern that masks, and there's clearly an overlap with the default mode network. The list of brain areas is really the left and right posterior cingulate, left and right angular gyrus, left and right frontal medial orbitofrontal cortex. So this pattern that I showed in the beginning in this video, I was saying, disappears. Statistically, in these large databases, this pattern appears less in people with autism. And another one that overlaps with the control network also decreases. So here we also see it here, and we see here how it strongly overlaps. So these are the only two that came out of this data. On different studies, here I do a small resume of the different studies I've been doing using LiDAR. So we find there is a healthy range of occupancy of these networks. We applied it to Human Connectome project data. They did several scans, so we find some reliability. If you have more probability of being in the global mode in one scan, it's more probable that in 2 weeks later, if you come back again, you will also have, so there's some fingerprinting there. But more important than that is to find changes, right? What is out of the normal? So we're finding disorders in major depressive disorder, in schizophrenia, in autism, cognitive decline, auditory hallucinations, obsessive compulsive disorder. It's not, so each one has different networks. That's why I'm not putting here all of them. Also, self-reflectiveness, relationship break, suffering from a relationship breakup. So there's something here that seems to be relating to these things. And then there are things that tune these values, which is important, right? One thing is to find they are altered, it has a biomarking potential, but then how do we tune them? And we're finding that psychoactive compounds strongly tune these modes, specifically, for example, the psilocybin affects only this lateral frontal parietal network, and it was replicated already in another data set from another group. We're finding that with deep brain stimulation, you can activate more certain brain networks and deactivate others. And also with natural stimuli, we also just have one with the long-term meditators that show more the sensory networks rather than the default mode and the frontoparietal, or watching smiling babies and music. This is evidence. Okay, and now it's the end of the evidence part. And the thing is, okay, we have all these works that are showing, I validated with these different methods. The method seems to be reliably capturing the same modes that people have been detecting. We see them visually, they are there. But what shapes these modes and where do they come from? Okay, and now here, there are 3 different mechanistic scenarios. Sorry, there's A missing there, but it will come. For why there are these, so when we see, for example, correlated activity between these areas, we could say, let me see if I can, yeah. Scenario A that has been proposed already for some time is that functional connectivity is associated with co-activations of this hemodynamic response. So what we detect in fMRI would be if a given brain area activates, right? Imagine even spontaneously through noise, since there is a structural connection between these areas and the neural activity propagates really fast, all the areas that are more connected to it will reveal correlated activity. So that was the thing. There were some models. I've been working a lot on that as well. What is this propagation across the structural network? We have like these dynamical units. As I said, we make them resonate at 40 hertz. I'm on these oscillations. We tried with the limit cycled oscillations, we like Kuramoto, with damped oscillations, perturbed with white noise, just for the mathematicians a bit. Sorry. Oh, where did the question? Okay, sorry. We use here, it's a coupled Stewart-Landau oscillators. We change different types of damping coefficients, but this is quite robust. When we perform this type of thing, we observe from time to time some groups of brain areas synchronize together, and when they synchronize, they can synchronize at different frequency ranges. Here is in a range of parameters where we see from time to time collective alpha oscillations, okay? We can see this, we call them these metastable oscillatory modes, like I explained a bit. And this generates slow power envelopes that shape patterns of functional connectivity. As you may, whenever they synchronize, those areas will have correlated activity. But it doesn't explain everything, especially one of them, there's different things, but one issue is that it doesn't explain concomitant, so at the same time you have a deactivation. And so before people were just looking at co-activation patterns, and now if you look at co-activation and co-deactivation, so there have been several works that have been proposing that actually what we are observing, these modes represent kind of excitation of harmonic modes of the brain. And these can be harmonic modes of the structural connectivity, so the Laplace eigenvectors of the graph Laplacian, or Pang et al., they use the surface mesh to estimate what would be the modes of resonance in that shape. But above all, this is an idea that explains this. And to test this, I was, looking at the signals from fMRI signals, the data usually is captured every 2 seconds. So we cannot see, sometimes when we see the next time frame, the mode is, we cannot see if it's really oscillatory, right? If there's an oscillatory mode. So I did some experiments on rats using ultra-fast fMRI to test this scenario. And so this is the recorded signals with ultra-fast. This is in real time. We see some patterns of activity that appear, that look like what is. So there is a consensus. This is a very summary slide of what was obtained, but that these patterns reveal resting state networks in rats. Okay, and here what I do is I decompose into principal components, so just the eigenmodes of covariance of this signal, and show that if we just do the linear sum of 10, let's say, standing waves, that's how we call them, in a way, the idea is that the resonance of an eigenmode would drive long-range correlations between brain areas and also anti-correlations. So without necessarily needing long-range inhibition or long-range excitation from different parts of the brain. Also, this idea is that when you superpose these different stationary waves, you can generate waves. And there was someone talking today about the traveling waves going in one direction or in another direction. If you just if you have 2 standing waves and you just change the relative phase, you can make them go in one direction or change the direction. So there are also, in this wave field theories, there's also, we also found that we calculate the resonance Q factor of each mode. We found that anesthesia increases the damping of this. This is like an approach where we, again, have these oscillatory modes, but they are macro scales. So it's not just a single unit that is oscillating, it's the wave pattern, the eigenmodes. This is just to say, well, this was published already last year, but now there is another scenario that is emerging, that we had a PhD student that we decided to test it. And this came in, this was just for the global mode, but it came in Science in 2019, that actually the global signal in gray matter was anti-correlated or negatively correlated with the CSF signal in the fourth ventricle. Okay, this was particularly in deep sleep. I will go here into this. We decided to explore this. So this was the paper that came out. Here is for me the exciting one of the signals, the plots that I found really interesting. So the gray signal is the average gray matter signal. So they put this mask and it's the signal in the whole brain. And then in purple is the fMRI signal captured with the same sequence, but just in a different slice, okay? In the ventricle, so they call it CSF because there's no neurons inside, so there's CSF inflow. And they really demonstrate that the fMRI is capturing also CSF inflow. Thing is that we really see there's a close relationship. Of course, they're not identical. It looks more like a something like that. It's still, there are different models trying to explain. But if they do the negative derivative of the fMRI signal in the cortex and the signal in the CSF, the overlap is almost identical, right? I'll say, okay, if we found that the global mode was decreased in people with poor cognitive performance. It was decreased in people with schizophrenia. We find it consistently the global mode. Could there be other modes? And then came in 2021, this paper really showing, so they applied it to a database of data sets from Alzheimer's disease, okay? Again, they take the gray matter, they take the CSF signal here in the ventricle, they show that it's negatively correlated, okay? Even at a 0 lag, there is a negative correlation. And here is this coupling between the CSF and the global signal. In healthy controls, it's quite negative, so it's minus 0.2. And then it becomes less negative. This is subjective memory concern, mild cognitive impairment, and Alzheimer's disease. But they had small numbers. The p-value was quite weak. But still, they also found there was a trend also with this is a gene associated with Alzheimer's disease. So the more genetic risk you have for Alzheimer, the less you have this anti-phase coupling between the signal in the ventricles and, okay. So this was just to introduce the rationale of this study. Then I was like, could the global mode that we were detecting with LIDAR be coupled with the signals in the ventricles? And then this is still a pilot study this is me inside the scanner, because I'm testing these ultra fast sequences but we do single slice acquisitions. But indeed I see like a global signal here in antiphase with the signal here. This is really the middle sagittal slice. If I have an axial slice, I can see like the signal in the ventricles negatively correlated with this. So in antiphase with the signal in the cortex. And yeah, so what we did was we took this ADNI database. So it's from the Alzheimer's Disease Neuroimaging Initiative, almost 600 scans from different levels of cognitive impairment. And I downloaded the raw signals and did the minimal preprocessing, retaining physiological components, which people usually remove, right? And we applied the LIDAR to the entire brain. So irrespective of anatomical location, I just have a mask. So all the brains are put in MNI in a standard space. We just put a mask of the entire brain, and we just ask which are the clusters of like patterns of phase relationships that we get. Okay, so if I just cluster into K=4, let me show you the mode number 1. I will zoom in then a bit later, but these are different slices. And this would be the projection in the eigenvector, but this time I'm taking the color code that they are using for these phase relationships for what would be gray matter and what is ventricle. So we clearly see not just but trust me, because this was then validated with some neurologists, but the locations of the fourth ventricle here, but also the lateral ventricle. So I want to show from the side. So these are sagittal slices, axial and coronal, to show that we get this. So we validate the previous findings. And we find, so this is the occupancy, remember this probability of seeing this global mode in controls, and then in early mild cognitive impairment, late MCI and AD. So it really decreases with AD, with cognitive decline. So it's something we say it's linked with cognitive reserve. Now, if we look at the other 3 modes, and now comes the exciting part. There's one mode that is found to decrease occurrence in the last stage of the transition to Alzheimer's disease. And then there are 2 modes that increase with cognitive decline. This one in particularly is the one that shows, so blue means it survives the Bonferroni correction, the arrows, but there is always this tendency to increase. So what happened here? If we look, I think I have a slide trying to zoom in. So here from the side, you see here the lateral ventricles, okay? Look at this slice. First, if we look at this slice, I think we can recognize a bit the default mode network that we were seeing before. But now, what seems to be happening is that those areas that I was saying that shift out of phase from the rest of the brain seem to be areas whose signals align in phase with the signals in the ventricles, right? So we see here their signal almost a continuum. From this one is healthy, it's the DMN, so the more you have it, the better. These ones are implicated with cognitive impairment already in the early stages. And you see that instead of the signal here being just going out from there, it seems to be something or relating with the fluid. So the signals in the posterior part of the brain are in phase with the signals in the ventricles, and here is at the bottom. So here I'm showing different slices. So it really seems that something is escaping. I don't know, let's see. If we look at the whole pyramid, so these are the p-values. So it's 4 orders of magnitude, these differences between controls and AD below the Bonferroni threshold, so 10,000 times more significant. So we have p-values of 10 to almost 10 to minus 8 compared to the ones from Han et al. Effect sizes, they go up to 0.7. So this is as we increase the number of states. But overall, from all here I try to color them to match them because it's the same network that appears, for example, for different Ks. So we find overall 5 types of brain ventricle coupling modes. And, okay, that seem to be related with cognitive reserve. So there is this one that was already reported in the literature. Okay, so this is the p-value effect size. So it really decreases. So it is more associated with cognitively normal, and it decreases with the progression to Alzheimer's disease. So the arrow indicates the increase. Mode number 2, if we just consider the voxels on the cortex and we overlap with the resting state networks, it reveals the default mode network. So I've been here trying to figure out what's going on. These ones have a worse overlap with different networks that have been reported. But for example, here, this one, the effect size is 0.70. It's really strong, the effect size between groups. And here we see again our executive control network, the lateral frontal parietal, strong overlap with it. If we look at it from the on the cortical level, it really looks like the one we detected in autism, right? But when we look at the entire brain, those areas whose signals shifted out of phase from the rest of the brain seem to be areas that are connected to the lateral ventricles and in phase with it. This is to show that these modes correlate. So the mode number 1, a little bit with memory and that, but mode number 2, this DMN, that we found also in autism, it's correlated with IQ scores. I didn't put everything, but it's positively correlated with memory, executive function, language, visuospatial abilities, also with age, but we correct for age in the statistics, so it's not, and even the Alzheimer's disease are older than the controls. And these ones correlate negatively with these scores. Here we just compared these 4, so the statistics were less stringent, but when we compare with all the 200 modes that we got, the network that most correlates with the memory score from ADNI, this is a composite score associated with memory, is this mode. So the mode that we detect for clusters 17, 18, and 19, modes number 6, 7, and 8, that are exactly the ones, the 3 ones that correlate, and 9 here, that correlated with the frontoparietal network. And then these other weird networks, this one negatively with executive function. So the more you have this, that again, when we have, so I sometimes have this, is this when we are just looking at the cortical surface or inflating the surface and neglecting the signals from the rest of the brain, are we creating illusions, like are we being like bullseyed to try to say this is neuronal networks, and maybe what these areas are coupled together is just they are gyruses, because it's the angular gyrus and the medial frontal gyrus, that maybe, I don't know if there's fluid inflow. And for example, people who have more of this pattern have less visuospatial abilities, and it's really a very asymmetric pattern that appears only for high K, then another one that correlates with age. I mean, I'm still don't know, but this, okay, to finalize, I wanted to show this. This is in, it's on archive. Just to let you know, it's in revision in Nature, so let's see how much it will go. But the thing here, so first of all, I've been questioning at the beginning, is okay, these patterns are driven by neuronal activity, or could it be the other way around, that they are interfering with neuronal activity? As we said, like if you have a neuronal culture, okay, we don't have proofs and experiments, but if you have a neuronal culture in vitro and you don't change the fluid, the CSF or the whatever, of course the neurons die on their own waste and their own toxic things, right? So you need to refresh the fluid. And if you bring a poof of fresh fluid into it, you'll see that those, in some areas, those areas will become more excitable. I suppose you change, I mean, I don't know. The idea is to incorporate this also. Question what we have. We assume that what we detect with EPI is only blood oxygenation variations driven by neuronal activity, but this is sensitive to changes in the magnetic field homogeneity. I try here to make an illustration of what this means. So when we have an increase in the signal, if the field is more homogeneous, when we send the pulse, it will take longer. So what this EPI sequence records is the T2 star is the decay time of when you send the pulse. So a change with respect to the mean. So this would be, it means that sometimes the field takes longer to respond to a pulse and sometimes take less. So it's interpreted as magnetic field homogeneities. which can be driven also by CSF flow. So this has been proven, and also by subtle spatial displacement. So I'm saying it's motion, but it's not like translational motion in the brain, but it can be something that they report also at tissue fluid interfaces. So it can create small displacements that create more artifacts or responses in the signal. But the thing is, well, they correlate with cognitive reservation, but then the thing is, we are not 100% sure they are neuronal, and that is one of my understandings now. I'm still a bit confused what is all this, but the idea is not to say that neurons don't play in the game. So the idea here that we still have the neuronal network, but in the models we had, we stimulate neuronal populations with noise, for example, with white noise. What if there is a structured noise or a structure of the background that I don't know, that kind of modulates then the activity, and that would be what shapes the fact that you have more or less, but still what governs fluid dynamics is unclear. But the idea would be that, yeah, there would be these modes actually modulate functional networks. This was a task. And well, so this was a project so Fulvia came to Portugal for 6 months from the University of Bari, that's her PhD supervisor. And we made this project. And well, here I'm at the University of Minho, funded by La Caixa. And that's it. Thank you very much.
So thank you for the interesting talk.